Yeah, you know, I mean, it's the same old story, right, in all statistics. Look, if you've got the assumed variance wrong inside of your model, then inference is going to be invalid. And I just kind of wanted to show you that it can go either way, right? I mean, the point is it's not always invalid in the sense that you have an increased type 1 error, quote unquote, or smaller than should be nominal confidence intervals. It can also go the other way, right? In other words, you should be doing conservative inference, which I don't know if I would say is just as bad, but certainly not what you want. Okay, I mean, I think when we err, we tend to be trying to err on the side of conservatism. That's not a political statement, that's actually a statistical statement. And so, but at the same time, you don't want to throw away information needlessly. And that's why what you're doing in the second part of this particular problem. So did everybody see something like this, where if you looked at type 1 error rates, in the 3 scenarios that I gave you, where I'm increasing intrinsic correlation with inside of the subject, and again, this is the repeated measures design in the sense that I have the same time, and so I'm measuring the subject under one condition, right, 10 times. So the OLS estimator is basically going to assume that what you're doing when you are measuring that same sampling unit 10 times under the same condition, they're going to treat it as if you sampled 10 different individuals, randomly sampled from the population. I mean, that's what's going on there. It's a independence across the region. Now, you're not really gaining that amount of information on the population, of course. And you can see that in the type 1 error rates that you get back and in the coverage probability that you get back. Luckily for us, we're dealing with an unbiased estimating equation, right? So all of those things looked fine. They came out unbiased as we've had before and we've seen before with the good OLS estimator. The problem really came when we said, oh, sorry, these guys. The problem really came when we said, what's the observed variance? In other words, that's the thing that we're really trying to estimate and have that closed form solution to the variance. Versus what the mean of our model-based variance estimates were clearly way off. That's going to affect coverage probability as tau squared is increasing. And it's also going to drive up type 1 error rates. You know, I mean, so this should be enough to tell you that there's an issue, right? I mean, in other words, you think you're making an error, quote unquote, 5% of the time, you're really making one 40% of the time, right? I mean, that's a pretty huge error. Okay.
So the coverage probability only depends on sigma score and tau score, not the tau score.
So coverage probability depends upon 3 things, actually, right? I mean, so this is what I've said in the past. The operating characteristics of a confidence interval that you put out are going to depend upon 3 factors. The first one is you have a consistent estimator, roughly unbiased, right? In other words, if you think about a wall-based confidence interval, is the pivot statistic, the thing that you're centering that confidence interval around, approximately unbiased, right? The second one is, now I take theta hat plus or minus z of 1 minus alpha over 2 oftentimes, right? But that z of 1 minus alpha over 2 that we're using is the reference distribution, so it's going to depend upon having that correctly specified. And it's going to depend upon square root of sigma squared, right? Or square root of variance, estimate of variance. Okay, so it's really all 3 need to come into play for a confidence interval. And unlike the type 1 error, so when you think about type 1 error and you think about computing the reference distribution under the null hypothesis, you only need to get the reference distribution right under one hypothesis. This is something that I think students don't kind of appreciate very much. A confidence interval, remember, represents the set of all null hypotheses for which we would fail to reject HO, which means I have to know the reference distribution under every possible alternative in order to have the correct confidence interval. Where that matters to us is when the variance is tied to the thing we're trying to test, oftentimes the mean. It means you have to have the correct mean variance relationship specified there, right? Because as my mean is moving away from the null, my variance is changing with it. You guys with me? So, confidence interval requires much more knowledge about what the sampling distribution of the statistic is because you need to know it under all possible alternatives. Whereas just a type 1 error rate only requires you to know that distribution under one alternative, which is the null, right? Or one hypothesis, which is the null hypothesis. Okay. So you saw that here on type 1 error rate, and you see again a similar concept when you move away from the null with respect to the coverage probability. So not a huge surprise on that latter part. Now, if you guys went and said, okay, now let me take a scenario where I observe or I sample the same sampling unit but under different quote-unquote interventions. And think of time here as like an intervention, right? So now I'm varying time with inside of the sampling unit. In that case, the analogy here is the case crossover design, right? Where when I use myself as a control, I observe myself under treatment and I observe myself under placebo, I can use the information on myself and I gain information from that correlation. It's like by design, you're controlling for all the precision estimates within inside of yourself to some degree, okay? Based upon that correlation with inside of the sampling unit. And so what we saw in lecture 1 then there was that in that case, relative to independently drawn samples of the same magnitude, we actually gained information. It looked like sigma squared times 1 minus rho. Right? That was our variance for the difference in the means. So as rho was increasing, that correlation within the subject, that variance is going down on the difference within means. Because again, I'm borrowing off of my own information as a sampling unit. So you see the same thing kind of start to play out now as you vary the covariate value with inside of the sampling unit. So now, when you treat everything as independent, you are not acknowledging the fact that you are using the same sampling unit as their control and gaining that information. So your mean model-based variance estimate is actually larger than what you would have if you had assumed independence in that case. You're ignoring the fact that you have this extra information. What does that mean? That means the coverage probabilities are going to be higher than their nominal level. They're going to be higher than 0.95. And it also means the type 1 error rates are going to go down relative to their nominal level. They're going to be less than 0.05. Okay? So again, it goes both ways. Both of these are things that you want to avoid. This is making conservative inference, so you're basically throwing away precision in your data. The other one is basically assuming that you have more information than you truly do. Right? So if you remember in lecture 2, I spent a bit of time talking about cluster varying and cluster invariant covariates. That's what you're dealing with here, right? So this is here a cluster varying covariate within cluster varying covariate. Time is changing within inside of the cluster. The other situation was a within cluster invariant covariate. It's not changing. And we're going to see this come up because it's going to affect our standard errors, whichever way it's going. Okay, so higher versus lower than, say, independence. All right. So the bottom line, though, is you need to build the variance here. It's the same story. Questions on that? Yeah.
So the observed variance for data 1 here in the crossover design is
Yeah.
constant.
The observed variance in the crossover design is constant.
And I want to know that's because essentially we're averaging out the effect of the random intercept.
That's basically what you're doing by using the same type of control. And Simon actually sent me a same question or similar question yesterday, and I was going to thank you for reminding me that. So that's exactly what's happening, is you're averaging over basically each subject's within the subject correlation at that point. So that is their random effect. Good. Very good. All right. Let's see here. Any other questions on this? All right. So now, so actually a few things. I'm just going to go ahead. You guys can just take this whole stack. How's that? There you go. Take one of each. There are 3 things there for you guys. As it's coming around, I will begin to introduce. Problem set 3 is up on the course webpage for you guys. You guys want the good news or the bad news? The good news is it's not due until May 8th. That seems like an eternity from now, right? May 8th, that is a long time from now. Almost is. Okay. That's the good news. The bad news is it's 4 pages long, but that's all right. It's because I gave a lot of explanation. Okay, so the very first problem, as this is coming around, you guys can start to look at it. You can look at it up here and follow along with me, though. So I labeled this Arsini special, because Arsini asked me a question discussion the other day, so you got a new homework problem now because of that. Well, it's going to be 3 problems. Thank you, Arsini. 4 problems. Everybody gets a little extra practice.
Yeah, that's so good right now.
So what happened was in problem set 1, you guys derive down the negative binomial model. And you did that by assuming a random effect, quote unquote a random intercept truly in that problem. And what you saw when you derived that down is you saw relative to a Poisson distribution that you were over dispersed, and that your mean variance function looked like mu times 1 plus alpha mu. And then in problem 2 of homework 1, I said, look, analyze the melanoma data and then fit a negative binomial model and do a likelihood ratio test of whether this thing is over parameterized relative to a Poisson distribution. That really comes down to saying I wanted you guys to do a likelihood ratio test of the null hypothesis that alpha is equal to 0 in that case. And in discussion, Arseny correctly said, look, I did some research and a lot of people don't use a chi-square 1 there, they use a mixture of distributions. Why is that? And the answer that I gave there, which is the correct one, which is because likelihood theory breaks down in that problem. Because you are testing a parameter value that's on the boundary space for that parameter. Alpha is positive in this case, and you're pushing the other case as boundary. One of our regularity conditions is that there is an open ball around the parameter of interest, the true value of that parameter of interest. And again, when you're testing HO there, you're conditioning upon alpha equaling 0. Right? So that is the true value under the null. Okay? And so, our usual likelihood theory would tell us that the reference distribution would be a chi-square 1 distribution, right? We're testing one parameter. That's what it would say to us. So that's what most of you guys did back in that homework assignment. And what I said was, it's going to be a little bit conservative. It's somewhere between a mixture of a quote-unquote chi-square 0 and a chi-square 1. So in other words, a constant 0 and then a chi-square 1 distribution. So you're going to be a little conservative in your inference here. But I said, don't worry about it at the time. Well, I want you guys to actually explore how much you would or would not need to worry about it. You're going to do it empirically. There's really not theory that will justify what the performance of this test outside of that regularity condition. So I'm going to have you guys write a simulation study where you're going to generate data that has a negative binomial formulation for the mean variance structure. So it's going to look like mu plus times 1 plus alpha mu. I want you to generate 5,000 data sets, and then I want you to, on each one of those 5,000 data sets, compute the likelihood ratio statistic for testing HO. And then go ahead and give me an empirical estimate of what the sampling distribution is, the reference distribution of that test statistic is now under the null hypothesis. Okay. So I've given you the mean model sitting up front, and then I'd like you to kind of compare that reference distribution that you observed to a chi-square 1 distribution. Okay. See how far they are off. You can just do that visually. Okay. Kind of give me an idea. Then you're going to get a little bit more quantitative in the sense of now, based upon those 5,000 simulated data sets, I also want you to estimate what the empirical type of error rate is now for that test that you're actually doing. So when you use a chi-square 1 reference distribution. So you're going to go through, you're going to actually perform a likelihood ratio test, you're going to tell me what proportion of time you reject the null hypothesis under HO. Okay. Then, since many of you guys are taking Stat 200C. You've been learning about things like power. And even if you're not taking Stat 200C, it's good to understand the concept of statistical power. So then I want you to actually look and explore what the power of the likelihood ratio test is for being able to detect over dispersion in this case. Okay. So my sample size that I'm giving to you guys here is 200. If you're bored, you really want to go above and beyond, you want to be the overachiever, then go ahead and vary the sample size as well and see what's going on there for the power, okay? But for right now, with n equal to 200, I want you to consider values of alpha equal to 0.1, 0.25, 0.5, and 1. And again, for those of you who are new to this concept of power, power is the probability that you would reject the null hypothesis under a specific alternative, okay? So power is a function of what the true value of that parameter is. Type 1 error is a special case of power. It's power under the null. Okay, it's probably rejecting each other under the null. The key thing that I want you to comment on here is, well, what kind of power do you have for being able to detect over dispersion relative to a Poisson distribution in a given set of data? If you say you had 200 observations and alpha was really 0.5, would you be able to pick it up? Right? If alpha was 1, would you really be able to pick it up? So if you think back to my comments about diagnostics, really when you're doing that likelihood ratio test, you're kind of doing a diagnostic. You're saying, well, am I okay going with a Poisson distribution? In other words, do I have over dispersion relative to that? All diagnostic tests really condition upon your current model. So in this case, they condition upon you having Poisson distributed data. And the thing that I've always tried to make you guys aware of is that you have to be wary of underpowered tests. And what that means is maybe you just don't have enough data or precision to tell you that you're different from what your assumption is about being right on the model. Okay? So that's kind of the whole point of having you guys look at power in this case. All right. Good. So the next problem is that we're going to go back to our correlated data setting, of course, and we're going to consider. I want you guys to start to learn to visualize what spaghetti plots start to look like under different correlation structures. Okay? And so you're going to simulate up data for me under a few different correlation structures. The very first one is going to be just a simple random intercept model. So each subject varies with respect to their intercept. So I have a B0I up there. Okay. I just noticed a typo though. This should be a little b. Make that a little b for me. Sorry about that. So you're going to simulate data up with different random intercept standard deviations here, and then plot spaghetti plots basically of those guys and visualize what random intercept spaghetti plots start to look like. And part B, you guys are going to extend that to saying, now let me assume random intercepts and random slopes. Okay, so now I have this B1I that's sitting here relative to time. So if you think about beta 1 being the slope of yi, or the trajectory of yi over time, B1I is now saying I'm allowing that trajectory to vary across individuals. Okay? Each individual has a subject-specific addition to the population mean trajectory. So there now we have a bivariate random effect in this case. So that's the notation that I used back in lecture 3. So you've got this covariance matrix D for the random effect. And what I want you guys to do is vary the value of D here. And again, create spaghetti plots to visualize what random intercepts and random slopes look like as you're varying them. And notice I've got different situations here. I've got situations where the random intercept is independent of the random slope, and I've got situations where the random intercept is negatively correlated in this case with the random slope. Why might you avoid making an assumption like this? Think about like the FEV example that I gave you guys, right? That was kind of the motivating example there. Would it be reasonable to assume that random intercepts are independent of random slopes? Think about what they mean for a second. A random intercept means a subject has a tendency to be higher or lower relative to the rest of the population when you start following them, right? And then a random slope means you have a tendency to have a trajectory that's higher or lower than the rest of the population. So assuming independence just says, look, where I start is independent of the trajectory of where I'm going. That's not often the case though, right? In other words, a subject that maybe is worse may be declining at a faster rate than everybody else. That would be positive correlation between the random intercept and the random slope. Or it could be that you might have almost a floor effect in the FTV. In other words, a subject that is worse really has no place else to go, so subjects that start high are going to start to go down quicker. That would be a negative correlation between the random intercept and random slope. Everybody with me on that? So again, making the assumption in their models that will make the assumption of independence between those two things often not reasonable. You often might have scientific knowledge about, well, if somebody starts high, they might tend to have a higher or a steeper or more shallow trajectory relative to everyone else. Okay. So we're going to get into that much more as we go on, but I want you guys to start to visualize what it looks like here in a known scenario where you're actually simulating the data. And then finally, the last one is, remember I said that we tend to parameterize the covariance structure in two kind of broad categories. One is the random effects model, that was A and B. The other is through serial correlation processes, which I talked about last time. So this is an exponential serial correlation process that we talked about. It's the continuous AR process from our last lecture. So I'm then going to have you guys generate data from that continuous AR process, and again, plot that out and visualize it. And the thing that I want you guys to really take into account here or pay some attention to is, can you distinguish this particular serial process from, say, the random slope and intercept process? When you start looking at these pictures, okay? And you're going to realize how hard our job is going to be for EDA for the correlation structure very, very quickly, okay? Because they're not to give away too much of the punchline, but sure, I'll just give it away. It's going to be pretty hard to distinguish between the two of those things. Random intercepts, you'll be able to spot it like that. You'll see variation at the starting time. But as soon as you start thinking about serial processes over time, it becomes extremely hard for your eye to pick it up with diagnostic flaws. Okay, good. So then problem 3, moving on, a little bit of motivation, is now going to go back to that random intercept and random slope model. And really what I want you to have is, this is now going to feed right off of today's lecture. I want you to investigate now ordinary least squares and weighted least squares, and what the impact is on efficiency when you have the correct weighting, or close to the correct weighting, and what the impact is on missing data. So that's something that we're going to have to start to deal with, right? So subjects might come back for a while and then they drop off of our study, okay? Or a sampling unit, you're measuring trees out in the forest, right? You're going along and then tree dies, okay? So you don't have any more measurements on it. So that's a sensor data case, but it's truly a missing data case. So what I want you guys to do is to see what the impact of missing data is when you have misspecified the covariance structure or when you've correctly specified the covariance structure. Okay. All right. You might learn a few things there. And then finally, problem 4 is more data analysis. So this will be discussed on May 8th when you turn everything in. It's going to be basically what I want is you guys to look at a cystic fibrosis data set. So these are children with cystic fibrosis. I talked about that a little bit more earlier in lectures, I think last one actually. So cystic fibrosis is a disease basically that affects lung function in children. And so we typically measure their disease progression by measuring FEV over time. You guys are getting used to that. And so what I want you guys to do is take a pilot data set of 100 subjects where we were considering their FEV and cystic fibrosis, and think about producing publication volume. Sorry to get you guys used to this, I'm going to start to enforce this much more. Summary statistics to characterize your sample. And then really the meat of this is to start thinking about, okay, what about EDA for a plausible model for the covariance structure? In other words, you've kind of gone through, you started to learn to visualize between random intercepts and serial processes. I'm going to teach you some more things about exploratory data analysis for the covariance structure. I want you to implement those things on this particular data set. And then finally, you're going to write down a model and fit what's called a generalized estimating equations model. So you're going to use a function called GEE, which I will introduce to you guys in the next couple lectures. And then I want you to extend that model to be able to simultaneously estimate longitudinal and cross-sectional effects of aging in this population. And that's what I ended last lecture with. I showed you guys one of the benefits of how you could take longitudinal data and you could decompose a model into saying what's the cross-sectional effect across the population of age, for example, on FEV, and then what is the within subject effect or the longitudinal effect of something like aging on FEV. So I want you guys to explore that here as well. Yes.
How is it different? Like, are they under treatment or?
These subjects are not on treatment. This is all pilot data just to characterize their trajectory now of FEV. So all I want to do is think about estimating the slope of FEV among subjects, but I want to do it well. In other words, I want to account for the correlation and covariance structure inside of a subject. Okay? So there's no predictor of interest per se in terms of treatment. My predictor of interest here is time. Okay, it's aging.
Yeah. So what I ask is like, how could it happen that when we just basically cross-section the population, there's one relationship of aging and FEV, and when we look at
That's what I want you to explore. That's exactly what I want you to explore. If you remember, I ended off last lecture by showing you an actual plot where you had a differential cross-sectional effect of aging. It looked like a positive association. And then within subjects, though, you have negative association, right? So, in other words, as I sample cross-sectionally from the population and take kids of different ages, I get one relationship across ages for their FEVs. But then if I follow the same child over time, I get a different relationship. That's exactly what I want you to explore. Okay. Good. All right, so we will leave it at that. You guys got almost a couple of weeks to work on it. So I would start sooner rather than later. Certainly you can get started on 1 and 2 quite easily now. So, and then go from there. All right. Other questions before we get rolling? Okay. I actually wanted to bring up one thing from last lecture. So recall in the last lecture, lecture 5, when I was talking about covariance structures, and I talked about serial processes. I brought up this slide and I said, look, if you think about the continuous autoregressive structure, exponential autoregressive model, as Tij and Tik start to approach each other, as these things become 1, I said, what is the interpretation of that assumption that this correlation becomes 1? And Arseni, I believe, answered the question. He said, look, that means that there's no measurement there. You're assuming that there is not measurement there in the process. In other words, if I could measure the exact same subject twice and do it at the exact same time, I will get the same result. Okay? And then Maisel asked a very good question, and she said, well, isn't that taken into account in the fact that you have the sigma squared that's sitting out there? And I gave an answer, but I didn't give as good of an answer as I would have liked to have given, so I want to kind of revisit it for just a second here. There is a distinction between sigma squared and the within subject measurement error. And what I mean by that is, when we think about sigma squared, if I gave you guys independent data, what does sigma squared imply? What is that? So again, go to 10 to 11. You guys have talked about the sigma squared concept, right? So this variance of an observation, your particular observation.
Inherent noise?
It's population variance, right? It's how much my measurement is going to vary after I've conditioned upon whatever fixed effects I have in the model, whatever subpopulation measurements that I have inside of that model, right? So that's between different, say, sampling units, just how much variation you have conditional upon those fixed effects. You guys with me on that? What I'm referring to here when we're talking about this measurement error is I've got the same sampling unit, and I'm going to take 2 measures on that same sampling unit, and I'm going to take them at an instantaneously quick place in time, and that correlation is going to go to 1. So there's a different concept between that measurement error, right, and just having variability in the population conditional upon fixed effects. So that's the difference here. Okay. So this model is making an assumption that if I'm taking 2 distinct measurements, but I'm doing them infinitely close in time, the correlation between those measurements becomes 1. In other words, I would get back the exact same value. Okay. So is that okay, Marisol? About a better explanation? Okay. All right. Now you guys know the things that keep me up at night. It's sad. It's very, very sad. I'm like, I gotta get a better explanation. Okay. So with that, then, we are done with lecture 5. I'm moving on to lecture 6. So in lecture 5, again, we talked about different models that people have used to try and, if you will, reduce the dimensionality of the problem in estimating the covariance structure. So different simplifying assumptions there. And the 2 camps, random effects, serial processes. Think about 2 large kind of models for doing this. There is the 3rd model, which says don't really try and reduce it at all, and we call that what type of covariance structure? Unstructured, right? In other words, I'm going to estimate every one of those off diagonal parameters and also the diagonals. When is an unstructured covariance structure going to be reasonable to start to entertain? I won't even say use, but start to entertain. Under what conditions? So by bigger sample size, you're really talking about larger number of independent sampling units, right? I'm not talking about the number of measurements on any sampling unit going larger, because that's just going to increase the size of that variance covariance structure. So that's one. But then what else? When have I've kind of stated it, and I've always stated it in the context of a particular type of quote-unquote design. Balanced and complete, right? The idea being that you have large amounts of information on every one of those covariance parameters, right? So in the cases where you might think about entertaining an unstructured covariance matrix and estimating all those parameters, you better start thinking about, I have balanced and complete data and I've got a lot of independent clusters. Otherwise, software will allow you to do it, but you might be estimating one parameter with one pair of observations, basically, as you're kind of going through, if you're in the incomplete or unbalanced design type. And things are going to get very erratic there, okay? So those estimates are going to not be converging to the correct covariance estimates, okay? So, I've talked about the unstructured, but do realize that it only really becomes useful with large numbers of independent clusters and balanced and complete cases. I have to bring this up because for whatever reason, one year I taught this course and I gave the final, and like 50% of the class, it was not balanced and complete. And 50% of the class came back and gave me unstructured covariance matrix. They said, this is the most flexible model that I can give. It's like, yeah, it's completely wrong. You know, I mean, it's like, it's way erratic. I would trust it in front of them. So that's why I'm emphasizing it now. Okay? Use it with caution. All right. Good. So now that we've talked about these things, let's think about estimation. And what I'm talking about today, which is weighted least squares, which is something that we all know and love, is the easiest place for us to start. But it is the most, it's the baseline case, I would argue, for what we would call a generalized estimating equation. Okay. So everything from this point forward for the next few lectures that I'm going to talk about is going to be related to what I call, or what we in the statistical literature call GEE models, generalized estimating equations models. Okay. And the idea is the estimating equation in that terminology comes from the fact that you're just starting to think about, I've got this Q up here that I'm going to derive an estimating equation from. In our case, the weighted least squares estimating equation is going to start with this guy. And the generalized portion of it is going to be, because it's going to be generalized later on, let's see, when you guys went from linear regression, the linear model, to the generalized linear model, what was the difference there? You allowed for discrete observations, you allowed for a mean variance relationship, and you allowed for a link function. So that's the generalized portion of this. So right now, so we're going to start with weighted least squares, and then we're going to build it up into generalized versions of that. Okay. All right. So back in our good old univariate days, if we wanted to do weighted least squares, I started in 2011 with this. So we had a mean model that looked like xi transpose times beta. Again, this is univariate data, so that yi that's sitting up there is a univariate response. We could start by saying, okay, I want to minimize the sums of squares, but I want to minimize a weighted version of that sums of squares. And you guys learned very, very quickly that the case where you would want to put a weight on this is when you had heteroscedasticity. And the ideal weight that you wanted to put on that was 1 over the variance for yi, each one of those guys. And that was because Gauss-Markov told you that that would get you back to the homoscedastic case, truly, if you transform the model by multiplying by 1 over the square root of the variance. All right. In the multivariate case, we can do the exact same thing. So I can formulate that guy, that sum of squared differences, or weighted sum of squared differences, but now I've got vector response yi minus the mean model for that individual. So now xi here becomes the ith observations design matrix. Then I've got wi, which is going to be now my weighting matrix in this case, yi minus xi beta. Okay? So again, exact analogy to what we've done before. We want to take wi to be some positive definite symmetric matrix. And again, ideally what we want to take it to be is going to be sigma I inverse in this case, capital sigma I. All right. So the estimating function that we would get from trying to minimize that sums of squares is just simply going to look familiar to you guys as being minus 2 times the sum of now the design matrix transpose for the ith cluster or sampling unit times wi my weight matrix times yi minus xi beta. Again, that nice form of just having being linear inside of yi. So this thing is just a weighted first order estimating function. You can think about it as, okay, going back to our Godam and 8 example. If you set that guy equal to 0 to obtain an estimating equation then and solve, you're going to get a weighted estimate of the beta hats. Because now it's just going to look like in matrix form here, since we're doing a multivariate responses, the sum over independent sampling units, design matrix transpose times weight matrix times design matrix, inverse times the sum design matrix transpose weight times yi. Looks familiar to everybody, right? It's just like good old weight least squared back in the day. Okay? Good. So the first classic example of this is, well, we can go through and we can throw OLS at this. This is what you guys did in your last homework assignment, where you looked at the variances. You just fit an OLS model. What you were doing was saying, I'm just going to take my weight matrix to be some constant variance times the identity. In other words, I'm going to treat every observation as if they are independent, both within and between sampling units or clusters. Okay? And so in that case, you get back what I'm going to refer to here as beta hat I for independence. Okay? And that's just going to look like your good old OLS estimator. All I've done is chunk it up though into the ith subjects or ith sampling units design matrices. Okay? And summing across that. It's just a little bit easier to write. Number one. Number two, I do this because now everything is conformable, right? Because in the cases where we don't have complete data in a balanced design, the dimensions of those yi's are going to vary, right? I might have 3 measurements on one subject, I might have 7 measurements on another subject. Everything here is conformable, as I've done this. Okay? It's all p by 1 at the end of the day here. Okay? Good. Well, if you guys recall back to 211 days, I think it was your first homework assignment there. I said, write down the ordinary least squares estimator as a weighted average of the response y's and tell me what the weights were. So in this case, if I hold my design matrix to be constant, so a balanced and complete, say, for example, like the polynomial growth curve model where I measure everybody at the exact same time, so I have the same design matrix. And if I hold my weight matrix to be constant, so I assume that my weight that I'm going to give to each observation is the same across my sampling units, similar concept here holds, right? My weighted estimator for the regression parameters simply comes out to be a weighted average of the mean of the response vectors y's. And again, it just gives you intuition, okay? What you're doing is saying, I've got this response vector, I can average those across the sampling units, and then I'll throw a weight on each one of them. The weight really comes down to being the leverage on the x's, okay, at the end of the day. I realize I'm using weight twice here. I've got W up here for weighted squares, but then you've got an overall weighted mean put on the left. Okay. It's going to be a function of the leverage and what you've measured there. Okay, so it's really just a regression, if you will, of the averages. So I can take the averages of my y's and then run the regression on these guys. Okay, so let's think a little bit about the moments then of the weighted least squares estimator. This is going to look very, very familiar to you guys. And then we'll see what we're going to have to deal with in practice to estimate some of these parameters that are going to come in elements. So first things first. Let's look at the first moment of the weighted least squares estimator in this case. Well, the first moment is going to look like the expectation of, again, it's a lot easier to think about things in terms of the independent sampling units and their contribution. That's going to look like xi transpose wi xi inverse, and then, inverse, times sum I equal 1 to capital N xi transpose wi yi response vector here. Okay, so that's just my weighted least squares estimator sitting up there. Well, the nice thing for us is, guess what? All of these things are constant up to yi. So this thing is just simply going to be equal to sum I equal 1 capital N xi transpose wi xi inverse sum I equal 1 to capital N, run the expectation all the way through. Expectation of yi. Well, the expectation of yi is equal to xi times beta, right? I mean, that's my mean model. I'm assuming zero mean on my errors. I've got an intercept in the model. So this whole thing then is just going to be beta. Okay? Because again, what you're going to get here is an xi beta. That beta is going to pop out to the right in this case to make things transformable. And so you're going to get cancellation of xi transpose wi xi times xi transpose wi xi. Okay. All right. So that's nice. Again, this shouldn't surprise any of us. We've seen this going along in the past, unbiased estimation. You guys saw it actually in your simulation study as well. Okay. Note that this is regardless of whatever weight I chose. Right? Wi here is just general. Could have taken it to be the independence matrix, could have taken it to be the true variance covariance matrix. No result holds. So now let's think about the variance though. So for the variance, what I'm going to get is, let's see, this thing's a constant. It's going to pop out to the left. Sum over clusters, xi transpose wi xi inverse. Then what I'm going to get inside is I'm going to get the variance of this guy. Well, that's going to look like sum I equal 1 to capital N, xi transpose wi, and then I'll have the variance of yi sitting in the middle. I've been calling that sigma I, right? That's just the variance of yi. It's the true variance of yi. Then a wi xi. And then finally, sum I equal 1 to capital N, xi transpose wi xi. And an inverse. So just to again emphasize, this thing is the true variance of the vector yi. All right. So this looks familiar to us, yeah? Yes, Steve.
So how come one of those isn't transposed?
How come one of which isn't transposed?
So left to the right.
This guy to the right? So this guy right here, what did I say about it earlier? It's symmetric and positive definite. This guy here, when you take the transpose of that, same thing is going to happen, right? Okay. Good. Okay. So now, if I take this guy and I'm going to call this AN, I'll put an AN inverse, so I'm calling AN this particular guy here. True variance sandwiched inside of the middle. And then finally, AN inverse on the right-hand side. Right? Comes back to what we've all been seeing all along, right? It's back to Hebrew white. Now it's the multivariate version of what's going on in the linear case. Okay? So, in this case, AN would be the Fisher information truly if we had assumed what? The correct distribution, but what would it have been? What would have given rise to the estimating equation that we started with to get this beta hat W? It would have been the Fisher information that would have arisen had I started off by assuming that my response vectors yi were multivariate normal, had mean x times beta, xi times beta, and had variance covariance matrix equal to wi inverse truly. You guys, you're going to see that come back up, but you should start to see that already appearing here, okay? So that's what would be happening. The reason why is because in order to just get A and inverse to be my Fisher information, everything else has to collapse. In other words, wi has to be equal to sigma I inverse, the true variance covariance matrix. Okay? So, just for completeness, that's what x transpose, or that's what A transpose times W times X. So across the plus. Okay. So, let's consider a few cases then. I'm just going to your next slide in your notes. So let's assume for a second that we took Wi to be the identity matrix that has dimension little ni by little ni. I'm just going to subscript it here with little ni, right? So that's the number of observations I have on the ith sampling unit in this case. So that's, again, what you guys did back in your last homework assignment. That's assuming that you've got truly independence within and between clusters, okay? The OLS model. So for that case, then, the variance of beta hat subscript I, again, the independence model, would simply come down to being sum xi equal 1, or sum over I, 1 to capital N, xi transpose xi. My w is going away. Inverse, what I will have sandwiched in the middle is going to be xi transpose sigma I, true variance of the yi's, xi. And then finally, I'll get the same thing on the other side of my sandwich. I equal 1 to capital N sum xi transpose xi. So now, again, take yourself back to 211 and 210 days. That looks very, very familiar to us now, right? That was exactly what we derived down in the univariate case. This is the multivariate version of that back in those days. If I had homoscedastic errors and independence across all observations, in other words, if sigma I was equal to sigma squared times the identity matrix, that sigma squared would pop all the way up, and I would get cancellation of that guy by that guy, and so I get something that looks like sigma squared times x transpose x inverse. You guys with me on that? Oops. Nobody let me, you guys didn't let me slide on that? Yeah, I didn't. Okay. Good. So, multivariate version of what we have seen and done in the past. The key thing is, and this is what you guys saw on your last homework assignment, is that if you're going to assume an independence correlation structure going in other words, do OLS, and you've really got correlation floating around, the true variance looks like this, but what R was giving you back in the OLS model is just a sigma squared times x transpose x inverse. Okay? That's why you were seeing that inflation of type 1 errors in the repeated measures case, and a decrease in precision, if you will, relative to the truth in the time varying case. And of course, we know from all the work that we've done in the past, what we would really love to do is say, well, what if I took Wi equal to sigma I inverse? In that case, you guys can just fill in the gaps here. It's pretty easy, right? If I have beta hat now, what I'm going to call sigma. So the true variance now is what I want by, or the inverse of that true variance covariance. That's just going to break down into what we would know and love, which is going to be xi transpose sigma I xi. And then inverse of that. Okay? Good. All right. I think in my notes I have a little sigma in So far, so good? Yep, okay. Very good, very good. So now, we know what we want to go for, and let me just make one more statement actually before we get there. What do we know about the relationship between beta hat sigma? You guys have it in your notes, so it's not a big surprise, but Gauss-Markov, the relationship between what I'm calling beta hat sigma there and beta hat I for independence. And what we're going to have is that the variance of beta hat sigma inverse is going to be less than or equal to the variance of beta hat I. And why can I say that? Why can I easily see that from Gauss-Markov there? Yeah. Oh, yes. My WI, right? Okay. Thank you, Mike. Now that we have that settled out, what can I say about the two variances of this estimate? Why can I say that? I've already said it. When you take that weighting to be sigma inverse, what is the variance covariance matrix of your weighted response now?
Just assuming,
So take this guy as a 1/2, right? Oops. Sigma inverse to the 1/2. Let's see if I can write this in some way that makes sense. There we go. What is going to be the variance of that guy? I will get this on the left. I will get sigma on the right, and I will get this on the right again, right, by the transpose. And so that thing is going to come down to be the identity, right? Which gets me back to what? Homoscedastic errors and independence, which Gauss-Markov told us already that that's going to have the minimum variance among unbiased estimators. So that means we know that this guy is going to be more efficient than this guy, okay? Go right back to Gauss-Markov, it's the exact same result, same thing, you would just prove it now in the multivariate. Okay? Exact same result. Okay? Good. So, with WI equal to the identity matrix, just to kind of close this out, we're going to obtain a beta hat OLS estimator where all of our observations are treated as independent they're equally weighted. And in this case, then, we have something that we can use, and that is that the expectation of beta hat OLS that we already saw, that will get us back an unbiased and ultimately consistent estimator of beta. So that's a nice thing. But what we know is that whatever we had done to get this unbiased and consistent estimator isn't necessarily the most efficient estimator. Okay? That's the problem for us. And so what we would like to do is try and gain back some of that efficiency. So again, if you take my standards on these things, you'd say, well, I want to start with a consistent unbiased, but that's great, I got one. Now let me try and build up from that and see if I can gain some efficiency back. Okay? So we may not be very efficient. And so for maximum efficiency, we want to weight by sigma inverse. idea. And again, same trick that we had before as we went through the 211 case in the univariate setting. All right, but now we've just got to deal with a slightly compounded problem with multiple parameters inside of that variance covariance matrix. Okay. Coming down. So that's basically what I have written on slide 6.8 for you guys as well, and just kind of outlining each one of those things as we go through. So now the thing is, of course, that in general, we don't know sigma I. It needs to be estimated. But if we've got balanced and complete data, we'll start with the very, if you will, the simplest scenario that we can get a handle on, right? If we have balanced and complete data, we can define up a simple moment-based estimator of what sigma I is, and then use that to obtain our weighted estimator. And here's what I mean by that. See if you guys buy this. So first of all, what are the asymptotic properties of these guys? Once I have a general weighting, well, the asymptotic properties are that my weighted ordinary least squares estimator is going to go off to a normal distribution. It's going to have mean 0 when I've centered it at true value beta. We talked about this. But it's going to have variance covariance. This is what we just talked about. It's going to be this limit of this sandwich sitting down here. That's exactly what we just started deriving. And I have it written up there, so I won't ask you guys, but if you wanted to prove this, it is the exact analogous proof to what we did for Lindenberg-Feller back in 211. Okay, but it's now the multivariate version of that, multivariate response version of that guy. Okay? So we did this very same thing in 211. We actually did the more general version of it. I kind of hand-waved a little bit about it through Huber-White though, right, for a general likelihood. So 211 you could have thought about as the normal case. The Huber-White case that I did in this class was for a general likelihood from an exponential family. Okay. Yeah, Mark.
In CW, you have an n sitting in front. Should that be 1 over n?
No.
So you're saying the variance goes to infinity?
So, no.
Cancel out somewhere.
No. Think about it for just a second, right? AN is summing over capital N, right? So this thing is proportionate to N, okay, as N is going off to infinity. So I have an AN inverse, this is like a 1 over N.
Okay.
This is like an N, this is a 1 over N. I gotta have an extra one in there.
Gotcha.
That's what that capital N is, okay? It's good, you gotta keep track of these things,
Yeah.
right? And then once I bring everything over, I get another 1 over N because I'm gaining information as capital N is growing on beta hat, right? Good, so good. All right. Okay. So now, here's the question though, is how can we provide an estimator from this just from what we know in the past? And again, here I'm thinking about a complete and balanced case for just a second. See if you guys buy this, okay? So if I assume that the variance covariance matrix for each of my independent sampling units is equal to some sigma. In other words, I'm not allowing it to vary, okay? It can have different off-diagonal elements. I'm not putting structure on them in that sense, but I'm assuming that it's the same from one sampling unit to the next, okay? So I just have this capital sigma there. Then we know actually that a consistent estimator of the optimal weight, well, a consistent estimator truly of the variance covariance is just to simply take the residual times the residual transpose and then divide by capital N, right? We know that because we follow large numbers again, right? So we follow large numbers on a multivariate setting. Each of those things, element-wise, is going to converge off in probability to the parameters of that capital sigma. That's great. Again, balanced, complete case. I'm gaining the same amount of information on every one of those. All the sigma i's have the exact same dimension. Okay? Good. So then, if we know that, oh, this is great, right? Can I do the following thing? Can I go through and I can start off and I can say, I'm going to fit an OLS model, and I'm going to get myself some beta hats. I'm going to take those beta hats. I'm going to get predicted values for my yi's, or fitted values for my yi's. I can use those then to come up here and estimate sigma I hat. I'll take that sigma hat and plug it in, get myself a new estimate of beta based upon that weight, and continue to do that until conversion. Sound pretty good? Sound reasonable? Guaranteed to converge? it is under certain conditions, certainly. What is this thing boiled down to? If I were to think about it in terms of a maximum likelihood estimate. This thing is going to converge down to the MLE, actually, in the case where I have complete and balanced data with the common sigma across every one of my sampling units, and I've assumed the yi's to be multivariate normal. This will be the MLE. That's exactly what it's going to come down to. So in that case, you will definitely get convergence, kind of this nice likelihood as you're going through. But the key thing is, and what I'm trying to get you guys to realize is that, and this is really the premise of generalized estimating equations, is the idea of taking this estimating function, realizing you don't know the weights, but using a simple moment-based estimator on the weights. Take what you've learned from the last iteration and create a simple moment-based estimator. And I've been trying to kind of get you guys to think about doing that all along. When I thought about estimating the row parameter in the Beatles example, I used a simple moment-based estimator, right? I just used the Pearson integral squared. That's my simple moment-based estimator. In the homework, when I estimated alpha, the over-dispersion parameter, I used a simple moment-based estimator. I didn't have to do it iteratively because my parameter values didn't depend upon it. But I just stuck in that simple moment-based estimator and said, okay, that's an estimator. I won't deal with maximum likelihood theory necessarily. Okay. Same concept going on here, but now we've got this iterative process because our regression parameter values are going to depend upon the weight that we put in. So we have to get that weight converged down. Okay. This shouldn't be too much of a surprise for you guys either, because you actually did this already in GLMs, right? You did it on the variance function. You got the fitted values, you plugged them in for the variance function, use those for the weights in that iterative weighted least squares process. Okay, great. Well, again, in the balanced and complete data case, if you've got this common variance covariance matrix, and if you assume multivariate normality, these will be the MLEs. And what that means for us then is that at the end of the day, the asymptotic variance of that beta hat estimator, you know that you've got a consistent weight, if this is true. Assuming sigma is equal to sigma is common across the sampling units. The asymptotic variance then of beta hat, where you use that weight, is just going to be 1 over capital N times what I'm calling C sub sigma inverse here, which just looks like your sum xi transpose sigma I xi. And again, that's because Wi in my method of moments estimator is converging off sigma I inverse, right? Okay. You guys with me on that? So now, Brian, though, to bring up this point, why the 1 over in here? And that's because I'm not talking about root in beta hat. I'm talking about just beta hat, the variance of that kind. So that's why I've got the 1 over in here. So going back to the previous comment. Okay. And again, does this guy look familiar to us? Sure. This is what everything would have broken down to. It's the Fisher information tree from the multivariate normal likelihood. We've got a common variance coverage change. Okay.
Is the algorithm?
What was that now?
Is the algorithm guarantee convergence if you misspecify sigma?
If you misspecify sigma,
Yeah.
we're going to talk about that today, like at 1 o'clock.
We are.
Not. You have to put conditions on it. You have to put conditions on it. And your guys' book, actually, the author names right in what order? Diggle, Liang, Hager, and Zager. Your book actually discusses a little bit of the convergence of the models, so if you want to read up a little bit more there, but I will also mention them when we get to the nonlinear case later. In the multivariate normal case, I can proudly say that it will converge. And, where you got to correctly specify. Good. All right. So now here's the trick, though, right? That holds if we've got a large number of independent sampling units, and where we have assumed that we've got a common covariance, and that assumption is correct. What that means, though, is, again, you need to have capital N be large for that method of moments estimator to work out, because really all you're doing, think about it, is you're just taking an average over capital N of these variance covariance matrix estimates, these empirical estimates that you're going through. By the way, the univariate case, what is this? Just to make sure that we're drawing connections. Good old MSE, right? It's the biased version of MSE. Okay. Sum of residual squared. So now, we need a large N in order for this approximation to work out reasonably well. If we don't have that, or if we're not in the balanced and complete data case, then this goes back to our last lecture. We might want to start to put some structure on sigma to avoid so many parameters, unknown parameters there, okay? And then try and get simple estimates, moment-based estimates of a simplified structure or assumption on capital sigma. So, let's look at one simple example here, and then we'll talk about how to extend this to other cases. So the simple example, probably the most simple example that you can think of, where you're going to allow for some correlation is what I've been referring to as either the compound symmetric or the exchangeable covariant structure case, right? And remember, this same structure arises from assuming what about a random effect model? I'm going to continue to hand you guys on this. There are equivalencies here. This is just, I can either come at this by simply saying, look, the variance of each one of my Yij measurements is equal to theta 1, and the covariance between any two of them is theta 2. That's the exchangeable concept. I can just say that, but this also comes from the derivation if you assume what type of random effect model. Just a random intercept, right? A simple random intercept also gives rise to this exact same variance covariance structure, okay? Okay. Good. So now, if I'm willing to make that simplistic assumption about what the variance covariance structure is, and I want to do the same procedure, I got to come up with simple moment-based estimators for theta 1 and theta 2, okay? So perhaps, and here I'm going to assume that I've got little n being constant. We can allow this to vary, and we will allow this to depend upon I later, but just from a notation standpoint, it's easier to do in this case in the balanced and complete case. What I can say is, okay, I want an estimate of the variance of any individual observation in my data set. Well, what I will do is I'll take all the observations within inside of each sampling unit. I'll sum those guys up, the residuals from that model, and square them. That's basically a sigma hat for the ith sampling unit, if you will. And then I'm going to average each of those sigma hats across the I independent sampling units. Seem reasonable to you guys? Yeah, I'm assuming they're all common, right? So every observation in my data set has variance theta 1. So I'm estimating the common variance theta 1 here by averaging over every observation in every cluster. Then, for the correlation between any two observations, I can say, okay, what I want to do is I want to take any two observations on the same sampling unit. There's going to be n times n minus 1 of those that are going to be distinct in pairs. So I'm going to average over all of the pairwise observations that I have for residuals. And then, so this is now within inside of a particular cluster, I've got an estimate of theta 2 hat. But now I've got independence across clusters, so I will average all of those as well. You guys with me? Good. So again, very simple moment-based estimators. These are just method of moments estimators. But again, the weak law of large numbers comes to our rescue in the sense that if we're correct in specifying this, these guys will converge off to theta 1 and theta 2. Okay, they're just means. Now, what happens though if you're wrong, right? This is a very big simplifying assumption. What are these things converging off to if you're not right? You've got to ask yourself that. Well, suppose for a second that the observations now each have variance sigma squared j. So the jth observation on the ith cluster has variance sigma squared j. In other words, I'm assuming consistency across independent clusters, but that the variance of that observation can vary within inside of the cluster. Well, where is our estimate, our simple moment-based estimator for theta 1 going off to in probability? It's going to go off to the average of those particular guys, right? So it's going to just average over each of my independent observations from each one of them. Okay? Where is my covariance estimate going to go off to? It's going to go off to the average covariance between any two observations, right? So these things may all be different on the upper triangular, but I'm going to converge off to what is basically the average of any of them. Okay? So I've assumed them to be constant. So in this case then, if we use a weight matrix where we take in our simple moment-based estimators and we plug them into sigma, and then we weight by the inverse of that, we're going to get the following at the end of the day for the asymptotic distribution. We're going to get a distribution that says, okay, everything's still going to converge off to normality. We're going to be centered at beta. That's all great. We've got a consistent estimator. But our variance at the end of the day is going to look something like this sandwich, starting to look familiar, A and inverse B, A and inverse. That's because we were wrong. We get X transpose WI, XI. The WI is coming from us assuming that exchangeable correlation matrix. Okay? But in the middle, we realize that, oh, that's really not the true variance covariance matrix. The true variance covariance matrix is something else that's out there, right? We were just wrong on whatever it is. It's going to read it in general. And so that guy is going to be sandwiched inside of our variance, the true variance there. Great. You guys with me on that? Sound reasonable? Good. Well, the big issue for us, we know this result. We can write down this result. Again, by the way, we have proven this result twice now. We did it once in 211 with the Lindenberg-Feller. We did it here with Huber-White. This is just a multivariate version of this. What we do not know now, we know the form of it, but we're still left with this. It's like we're right back to where we began, right? Well, if I knew the true variance of yi, I would have used that for the weight to begin with. We don't know it. So what are we going to do at the end of the day? We're going to empirically estimate it. Okay? So we're going to take a BN, what I'll call